So roots of unities, that's the solutions, and omega, it's a Greek letter omega, if you don't know, a little one. It's a very typical name we often use to distinguish or denote those roots of unities. So roots of unities of order n, that's the solution to the equation like this. In real numbers, we have only, how many solutions we have in real numbers? Oh, 1. Yes, thank you. 2 or 1, depending on the whether n is odd or even, right? When n is odd, we have 1. When n is even, we have 2 solutions. In complex numbers, we have a perfect picture. Every time we have n solutions. It's the perfect beauty here. You know, just you don't have to make any exceptions. And if you want to come up with those solutions, you have to follow the steps we did just with the previous example. First, we convert this number 1 into the exponential form. It's a very easy conversion. Here it is. And I already introduced these steppings. You see why my index k here. For different case, it will be different conversion, but all of them are acceptable. And then if I go under for the root, here's my root. And my steppings, again, I will choose the sided version of the indices. So k will be 1, 0, 1, and all the way to n take 1. Sometimes you can choose the symmetric one. You can start with this, I would say, negative. You can start with a negative n take 1 on 2, in case it's an even number, and do. Yes. Geometrically, it's the same picture. The roots of unities, they will go to the vertices of perfect, this time, well, this is a picture for n equals 7. So it's a 7 gone. They'll be looking like this. The angle between the adjacent vectors will be this angle. As you're stepping, the real and imaginary part will be cos and sines of those angles, which are not easy to find, except for a very limited number of cases. For instance, n equals 5. Now we know how to find that, cos of 2 pi and 5. So this will be my... This is the first value, omega 1 from this list. This is the value omega 2 from this list. This will be omega 3. This one will be the one before the last one. It will be omega n take 1. And the very last one, the unity itself, which is always a part of this solution, it will be omega n. You can see this dichotomy which you observe in the real case. When n is even, one of these vectors will go on the negative side. When n is odd, you will have them symmetrically around the negative side. That's why you don't have negative 1 as a solution. When n is even, you do have negative 1 as a solution. Right. Now, the question 42 itself, it doesn't say to find the roots of unity. No, it's just like a preliminary introduction to the question 42. Question 42 itself says this. It says, imagine you have one of these solutions, doesn't matter which one, but you have the one where k is not equal 0. Well, I think you can argue right now because my indexing my indexing on this diagram doesn't correspond to my indexing in here. Do you see that? The indexing on this diagram for the omegas I put, it doesn't correspond to the indexing in here. The indexing here starts with 1 and finishes with n, whereas my indexing starts with 0 and finishing with n take 1. So if I want to make this consistent, I have to re-index this to 0, yes. Yeah. Or otherwise I have to change this from 1 to n. Both ways will make things consistent. I'm sorry, but I chose this one. Now the question 42 says this: taken one of these roots of unities, one of these, but specifically not the one which is for k equals 0. So the one which is not unity itself. So take the one which is non-zero and prove that the sum of the powers of this particular chosen root of unity is 0 all the time. So this is something we have to prove. Now the solution itself is just, it relies on the knowledge on one identity, which is, well, if you're not aware of that identity, it relies on formula for the sum of the geometric progression, in fact, because this is a geometric progression, right? We have a number which we take to the power, consecutive powers, and add them up. So basically, we can sum these numbers with the help of the formula for the sum of the geometric progression. However, I mean, I personally like different way of framing this. It's basically this. Essentially, it's the same thing. It's the sum of the geometric progression formula. But I'd like to personally, I like to write it something like this. This is the sum of the geometric progression formula. Look at this. If you take any complex number, here's the sum of the powers. Here they are. If you solve for this second bracket, if you divide this right-hand side by this extra factor on the left-hand side, that will be exactly the formula for the sum of the geometric progression, finite sum of the geometric progression. All I did, I just took the denominator here, in the formula you know, and I put it here as a factor. That's the way I like it. I mean, it's not a big difference, so I can't even say I like it more. I just type it like this. And that actually was a rather silly thing to do, because right now the next step which I'm going to do, I'm going to actually take this factor here. So you can say I wasted lots of time typing this one. So if I use this formula, or if I use the sum of the geometric progressions formula, which is the same as this one, it's just with the minor rearrangement, then this sum, or I call it the left-hand side, I can replace with the expression like this. Here's the 1 take z to the power n, where in the place of z we have this omega k, and here's the 1 take omega k. At this stage, you understand why we chose the omega k like this, because otherwise this denominator will not make any sense. But for any omega k which is not unity, this denominator does make sense, and the fraction will be 0, because omega k to the power n, it's something which returns unity. So here will be unity, take unity, and the result is 0. And that's all there is to it, in fact. I mean, even though this question is marked with H, that's all there is to the solution of it. Now, any questions? I can take this question a little bit further, because what I can do now, I can bring in the Euler formulae, and via Euler formulae, the real and imaginary parts of these numbers, they will be cosine or sines of these angles, aren't they? So if I equate now the real part here to 0 and the imaginary part here to 0, if I do that, this extra step, which is not part of the question 42, but still it's a nice step to do, I will come up with what I call a corollary. Nice, beautiful corollary, which says that the cosine, sum of the cosine of multiple angle alpha, where alpha is this particular angle, is 0, and sum of the sines of the multiples of this angle alpha, this angle, quotient of 360 degrees by n, sum of the sines of these angles is 0 as well.